Okay, shall I start?
Yeah, please.
Okay, we're used to the idea, right, that quantum mechanics is important for cosmology, notably in the production of small quantum fluctuations very early in the universe and density that grew under the action of gravitational attraction to make the large-scale structure that we see today in the CMB and in the galaxy-galaxy correlation functions and so forth. But my talk is not about what quantum mechanics does for cosmology. It's about what cosmology does for quantum mechanics. And that's because, as we'll see, I will describe how ordinary quantum mechanics that we read about in textbooks has to be generalized to apply to cosmology and to what impact that generalization has. Now, when quantum mechanics was developed in the late 20s of the last century, there was another big major thing that was happening, and it was triggered by the discovery that the universe was expanding. I note here these famous people, the Abbé Lemaitre, Hubble, and Vesto Slipher, who's the person that discovered the redshifts. And here's Hubble's very first Hubble's law of velocity versus distance, and that's the linear relation from which he deduced the Hubble constant. Now, I think it's fair to say that textbook quantum mechanics, the quantum mechanics of measurement situations that we use in the lab, is the most successful theoretical framework for prediction in the history of 400 years of physics. And yet it has to be generalized to apply to cosmology for a number of reasons. First of all, Copenhagen quantum mechanics, or the quantum mechanics of measurements, assumed a division into observer and observed. But in a theory of the whole thing, cosmology, there can't be any fundamental division into observer and observed. It assumed that the outcomes of measurements were the primary focus of science. But measurements and observers can't be fundamental in a theory of the early universe where neither existed. And it assumed that the classical world that we see all about us was external to the framework of the wave function, the Schroedinger equation, and ordinary quantum mechanics. But fundamentally, there are no variables that behave classically in all circumstances. But even worse, it wasn't possible to retrodict in Copenhagen quantum mechanics. You could predict the outcome of experiments, but you couldn't go backward in time. That's because Copenhagen quantum mechanics was based on two laws of evolution: unitary evolution by the Schroedinger equation, when the system was isolated, that can be time reversed, right? This could be run forward and backward in time. But it was also had a so-called second law of evolution, which was projection or collapse when the system is measured. That only works one way in time. The evolution is from the wave function to the projection of the wave function on the output of the measured quantity, and that is not time reversal invariant. So you can't retrodict in quantum mechanics, but cosmology is all about the past, right? We reconstruct past history in order to improve our predictions in the future. But those retrodictions are important for, because we retrodict back, for example, to the Big Bang, right, which is the origin of the CMB and so forth. We retroact back to the description of the formation of structure by the collapse of small fluctuations and the growth under gravitational attraction. We retrodict in order to understand Big Bang nucleosynthesis and reheating. and on and on. So retrodiction was essential, but it wasn't available in the ordinary textbooks, quantum mechanics. Now, not all retrodictions are useful. Here's one that isn't. But there are many that are, as I've just outlined, that are necessary for us to understand our present situation. So textbook quantum mechanics, to incorporate things like retrodiction, has to be generalized for cosmology. We now have such a generalization. Here's a brief history of it. It started, I think, with Everett's insight that his observers were physical systems within the universe, not outside it, subject to the laws of quantum mechanics, but not playing no special role in its formulation. The formulation we wound up with, which I'm not going to describe in a huge amount of detail, is called Decoherent Histories Quantum Mechanics, or Consistent Histories Quantum Mechanics. And it's the work of a great many people. Some of them are here. This is Bob Griffiths, who certainly played an important role, right? And this is Gell-Mann, and I could even put my own picture up here, right, if necessary. It's not something that's new, right? It's about 30 years old or so, and it's a way of looking at quantum mechanics that doesn't stress, it stresses histories of things, time sequences of things, rather than measurements. So it's not some radical thing. And I can describe it to you in better in a simple model. Well, I also should mention that it's now become fairly standard, right? If you read, for example, Weinberg's textbook on quantum mechanics, it's all decoherent histories, right, in some chapters. As a little model, let's neglect quantum gravity for the minute and just consider a model universe which is in a very large box, say 20,000 megaparsecs on the side, right? Everything is in the box. You, me, stars, planets, suns, observers, their apparatus, and so forth. Nothing is outside looking at the box. In order to discuss that, there are sort of two theoretical major inputs. One is a quantum theory of dynamics, which I just denoted here by the Hamiltonian age. The other is the quantum state of the system, which I've denoted here by psi. And those two, this is supposed to be an Abrahamic cat, right? Those two things are sufficient, right, to make predictions of probabilities of history. So here's the theory, H and psi, whatever they are. Here's what, in that little model, what we do with it. The most general objective of quantum theory in general is the prediction of probabilities for theory, for histories of things. The Earth goes around the sun on, of course, a classical orbit. But in quantum mechanics, there's no certainty that goes around on the orbit we like. It could go around on any orbit. It's only a matter of probability that the one we have has a high probability. So extrapolating to cosmology, what we're interested in are histories of the universe, cosmological histories of space-time geometry and matter fields. So it's not a quantum mechanics of measurements, it's a quantum mechanics of histories, sequences of things in time. Right? And because you can have histories that extend backward in time, that is, you can therefore use quantum mechanics to make retrodictions in a way you couldn't do with quantum cosmology. I'm just showing this way down at the bottom. first person to realize this was Einstein. And here's a quote from his paper with Tolman and somebody else. The principles of quantum mechanics must involve an uncertainty in the description of past events, analogous to the prediction of future events. But in predicting, interference is an obstacle to assigning probabilities to histories. By that, I mean quantum interference. You see that very clearly in the two-slit experiment. Here's a two-slit experiment. There's an electron gun on the left, right? A screen with two slits on it, an upper slit and a lower slit, and a detecting screen where you detect the particle. Of course, if you take the sum of these, you get the characteristic interference pattern when you square it. But that interference pattern is not the sum of the squares of the amplitudes for these given histories. It would be inconsistent to assign probabilities to the individual histories. You need to do the sum. So a rule is needed to specify which histories can be assigned probabilities and which cannot. In textbook quantum mechanics, we assign probabilities only to sets of histories that have been measured. Of course, the measurement destroys interference. But in decoherent histories, probability signs are assigned to histories that decohere, for which there's one reason or another, there's a negligible interference between members of the set as a consequence of H and psi. Decoherence, the absence of quantum interference between histories, is a more general, more observer-independent rule than assigning quantum mechanics to measurements. It means, for example, that we can assign quantum probabilities to the position of the moon when it's not being observed. Nobody's looking at it. It means we can assign probabilities to density fluctuations in the very early universe when there are no observers around and nothing to measure. It means we can discuss, in principle, the systems that were important in the earlier quantum mechanics, that is the complex systems like measurements, the brain. We don't know how to do that, right? But in principle, it should be possible. So it's simpler than ordinary quantum mechanics. Furthermore, decoherence is very widespread in the universe. It's not something that has to be engineered. It occurs all the time. And here's a classic example, I think, basically through the Osum early on. It's one dust grain. I'm drawing a picture of one dust grain here in a superposition of two positions a millimeter apart. I never know how to draw a superposition, but this is the best I can do. They're a millimeter in size, a millimeter in part, and they're out in empty space. They're still decohered. The interference vanishes. The relative phases vanishes in an order of a nanosecond just from the microwave background radiation. So decohering situations are all around us, and as maybe was evident from Neil's talk, you actually have to work hard to find a situation which is not decohering and which can exhibit the quantum interference. Measurements are an example. In a measurement situation, here's a picture of one, somebody measuring the which slit an electron went through, right? Here's a screen with two slits, and there's a bunch of measurement situations, an observer. A measurement variable is not normally decoherent. Measurements decohere because a variable not normally decohering becomes coupled to a variable of an apparatus that doesn't decohere because of its position in the universe. For example, all the scattering that occurs with this. So Copenhagen quantum mechanics is therefore an approximation to decoherent histories that's valid for measurement situations. It's important to emphasize that we as observers are just another system in this, not preferred in some way outside it, experiment has extended the sizes of systems for which the superposition of macroscopically distinct states can be seen. For example, here is this is work of Lisa Hackenmuller. Here's the experimental large biological molecule of fullerene. Pass that through the two slits, and indeed, you get an interference pattern despite the size of this. But we won't see an interference pattern or feel it or something that we're a part of, and we are a part of a vast superposition that's in the universe. But somehow we have to get back to classical physics. A quantum system behaves classically when it's stayed in Hamiltonian, predict high probabilities for histories with correlations in time, governed by deterministic laws like Newton's laws of motion. That's true for example, the flight of a tennis ball, for the orbit of the Earth around the sun, and for spacetime. We don't generally have spacetime, but we have classical spacetime. We don't generally have classical spacetime, except in situations where it can be appropriate coarse graining and decoherent. Now, one of the great features of our quantum universe is its quasi-classical realm, the wide range of time, distance, and so forth, where the classical laws of physics hold. How did it come to be if it's all quantum mechanics? So a formulation of quantum mechanics that does not posit the classical quasi-classical realm has to explain it as a feature of our specific universe from its particular initial condition, its particular sign, its particular state and dynamics. Here is a very rough run through of how it works. You start in the beginning with the state of the universe and quantum gravity imply some region of classical spacetime, coarse grained classical spacetime. That is, histories of geometries correlated with the Einstein equations. Local Lorentz invariance implies conservation laws, conservation of energy, momentum, you also have conservations of numbers. Sets of histories conserved quantities are conserved by the action of, for example, various environments that interact with, are decohere because of the actions of, because they're approximately conserved. Approximate conservation implies also that the variables are predictable despite the noise from decoherence. Then if you generate up the local equilibrium, right, with continua, you get the equations of motion defining correlations in time. But all this means that our quantum universe has some state. The question is, what is it? That's the objective of quantum cosmology. But it also means that contemporary final theories, to use Weinberg's phrase, have two parts, a theory of dynamics and a theory of psi. So you can ask two questions. First of all, which regularities come mostly from H and which from psi? And do we have here an unfinished task of unification in these two parts? Here's just a rough idea of what comes from each part. From the dynamics, comes classical dynamics, laboratory experiments, i.e. everything that goes on in CERN. But regularities in the universe that follow mostly from psi are regularities in time, right? That means classical spacetime, the early homogeneity and isotropy, and plus inflation, the fact that fluctuations begin in their ground state, which we see later on in the CMB, arrows of time, the fact that in a time-symmetric dynamics, we have arrows of time in the universe. All that comes from basically its initial condition, the existence of the CMB, large-scale structure, isolated systems. Why do we have them at all? Right? We don't have them in the early universe. The topology of space-time, maybe the number of large and small dimensions, number of time dimensions, and the coupling constants of effective theories. Well, here's a locally popular namely popular by me, right, theory of a quantum state of the universe. This is the no boundary quantum state of the universe. Here's a picture of Stephen and me who worked this out. It's given by a path integral, presumably like, now I risk myself here. I wrote this path integral down with an e to the I. Neil would like to see an I in here, right? And maybe that's right. It's also been extensively worked on here in Moscow by Barvinsky and Kamichuk, right? And here's a picture of their density matrix that they use it, two no boundary wave functions back to back. In the semi-classical approximation, this means that the wave function is given by roughly e to the I times an extremum of the geometry. So it's easy to calculate and it's easy to predict. But all that is in a box with no quantum gravity. If we want to get beyond all this, then we should somehow include quantum gravity. So familiar quantum theory assumes, like Copenhagen quantum, or what I called the Copenhagen or measurement quantum, assume the fixed classical spacetime. We need that just to find what the T is in the Schroedinger equation. But in general, quantum mechanics in a quantum gravity spacetime is non-fixed. It'll be a sum and a path integral of different amplitudes where a given point may be space-like related to another point or time-like related to another point. That's because in quantum gravity, space-time geometry is fluctuating without, so something beyond decoherent histories is needed for quantum gravity. The key idea, I think, is this, that histories don't have to describe evolution in space-time like we're using, in a fixed space-time like we're using, but they can describe evolution of histories of geometry as well as what goes on inside. We can probably make a generalization of decoherent histories quantum mechanics in a four-dimensional space-time by including the following elements, specifying, first of all, the fine-grained histories of the system, which are histories of space-time geometries and matter fields, what the relevant coarse grainings go. That means partitions of coarse-grained histories in the four-dimensional diffeomorphism invariant classes. That's still an open question, how to do that in a four-dimensional diffeomorphism way. And then we need a measure of interference, a so-called interference functional or decoherence functional defined by four-dimensional sum over histories. I'm not going to exhibit any of that, not least because it's not all worked out. At any rate, it won't have any equivalent 3+1 formulation in terms of states-like surfaces. So the usual quantum mechanics of a Hilbert space of states evolving unitarily through a family of space-like surfaces requires a classical space-time to define those surfaces. But we don't have classical space-time everywhere in the universe and for all times. Not near the Big Bang, cosmology again, maybe not in evaporating black holes. Rather, classical space-time and usual quantum mechanics, textbook quantum mechanics, emerge together from something deeper. I have ideas of what the something deeper, but that's a question on which I'll end. There's much to do in the next 90 years to work out the consequences of cosmology for quantum mechanics. Thank you very much.
Okay, thank you, Jim. So now let us get to the questions. Philip Stamp.
Hi,
No
Jim.
questions?
Yes, I have a question.
Universe and there are no questions?
Yes, I have a
want to ask
question.
the question, if possible.
Can you hear me?
Now
I'm
I
a little
hear you.
faint. I'm going to turn up my volume, which means I have to get out of this. Okay, now try it.
Can you hear me
Yes.
now?
May I ask a
Now I
question?
can hear. Now I can hear you. I have to turn it down a little bit.
Do you hear me?
I do hear you.
Oh, yes.
Let me know
Thank
when
you.
you'd like me to ask the question.
Yes, I have a small question.
Sorry,
I see that-
what is going on here? Sorry, I was asked to ask. I was asked by to ask a question. Can I do that?
For who?
Please go ahead.
Okay.
Okay. So my question is the following, Jim. When you were talking about this a long time ago, you actually looked at the question of achronal regions of space-time and the necessity to abandon a Hamiltonian framework. And of course, people like Kip Thorne looked more at this. So could you comment on how you see that being discussed in a decoherence functional framework?
It's the same way. Of course, it's more complicated to construct a reasonable decoherence functional, but I described, I believe, how to do that, right? So that work is still there, but of course, I didn't talk about it today.
Sorry, which work is that? I'm not aware of any discussion of decoherence functionals for achronal space-time regions.
Well, I did write papers on achronal space-time. I have to look back and see whether I exhibited a decoherence functional. If not, there's a problem for you.
Okay, because that seems to me to be a very interesting question in the sense
So
that—
first of all, who are you, so I know who to?
This is Philip Stamp. I don't know what's going on with the—
Oh, I know. No, I see you when but because I'm sharing my screen. Oh, there you are. You're in the middle.
Well,
Yes.
I guess the point
I'll
is
see if
that—
I can find that achronal spacetimes.
Yeah, I mean, I guess the point is that we know that in the case where you do have achronal regions of space-time, even a simple path integral has very peculiar properties. This was the work of Thorne et al. And others.
Yeah, let's see. There was work by, let's see, Laflamme and some other, I've lost track of the history of it, but I could probably dredge it back up.
Okay.
But I'm not going to work on it. I've got other things to work on.
Okay, I'd be interested to know other papers that you wrote.
I'll try to find them.
Okay, thanks.
At this stage in life, I don't go off just working on any old thing. I've got a program which is largely getting my work out. But I'll write you, Philip.
Next question from Alexei Starobinsky.
Okay, thank you.
Wait a minute, where is Alex? Right?
Okay, I'm here now. Okay, sorry. Thank you, Jim, for your very interesting talk. My remark is what we are actually doing now in cosmology, especially in numerical simulations. Nobody assume that the space-time is deterministic. Actually, what is done in body simulations that perturbations are assumed to be intrinsically stochastic quantities, and this results in a very good agreement with observational data. So, do you consider this as a partial step just into the direction which you described, that it's indeed that we have already made a transition from considering the space-time as completely deterministic? As I said, it is still C number, but intrinsically stochastic. So, is it, according to your opinion, is it a correct step to your
have a stochastic quantum mechanics? Whatever works. I can't see when I'm having a hard. You're breaking up a little bit. You might have to send me an email with the question. right? Because I'm only hearing words like that. But let me just quote Chairman Mao. The journey of 1,000 miles starts with a single step, or maybe steps. That's what I'm doing.
Okay.
Okay, Jim, maybe I missed something in what you are proposing, but when you say that a generalization is needed of quantum mechanics, because we don't have a sequence of classical three geometries, so what is missing from, say, approach that Neil was discussing and that you were using yourself, that when you take a path integral over all possible space-time histories, including matter and geometry histories, and you can also talk about histories there, right? Which decohere. So why do you need generalization?
We need a generalization, I think, just because it's not ordinary Copenhagen quantum mechanics of measurement situations just to do retrodiction.
No, Jim, this is not what I'm asking. I understand that we need generalization to go from Copenhagen to decoherent histories.
Okay, good.
But I thought that you are suggesting that we need generalization beyond that. Is that what you said? Or?
That's true, although I put forward, although it's buried, I intend to, one of the things I'm doing is I have to get ideas out, sort of generalized quantum mechanics is what I call it. How you could have a whole class of quantum mechanical theories, right, that were based on the principles of decoherence, fine-grained histories, coarse-grained histories, a measure of decoherence, and a notion of coarse graining. Now, some of those are still absent, right? We don't understand, for example, how to, in a four-dimensional diffeomorphism invariant way, how to coarse grain histories, right? That is, to bundle fine-grained histories up into into sets. Although we're certainly doing that every day, right? As I look around the space-time, right? It consists of probably a huge collection of fine-grained histories with certain weights. That would be, for example, possibly helped by what Neil is doing. So, okay. But we don't have a four-dimensional diffeomorphism invariant notion of coarse graining yet. We could get one, and I explored this a long time ago, using lattice methods based on the Reggie calculus. But I don't know, somehow that isn't all that satisfactory either. And I can also do it in linearized gravity, right, very effectively, because you can calculate the true physical degrees of freedom. One of the projects is to write that up, right? So the pandemic has been very useful to me. I'm doing nothing but writing papers.
Please, can I ask the question?
Yeah.
Yes. Is it possible? Do you hear me?
Let's see.
I do hear you.
Who is that?
Boris Altshuler. I want to ask the question.
I can hear you. I can't quite see who it is, right?
It's Boris Altshuler. Yes.
Okay.
Yes, thank you. The point is that, of course, you're right that in the closed system like universe, the coherence must substitute the notion of measurement. But my question is, in functional integral, there are no mathematical tool for coarse graining for decoherence, dynamical. So what may be the description of decoherence exact? I know the only way to produce decoherence is to separate artificially system for two parts and make an average over so-called unobservable part. Perhaps the mega universe, when radiation comes to behind the horizon and becomes in principle non-observable for our universe. Perhaps it's the only way to make dynamically the coherence in the early stages of the universe.
I don't know, but I think I agree with you.
But what is your mathematical tool of the coherence?
It's a work in progress.
Okay, the last question from Andrei Barvinsky.
Well, I remember, Jim, that among your possible suggestions for generalized quantum mechanics was such a model when you had two density matrices. One density matrix at the beginning of the set of decoherent histories and another one in the end.
Right.
And the question is the following. It would seem that in your discussion of possible applications of this quantum mechanical concepts to cosmology, to the universe as a whole, you somehow disregard the possibility of such an extension, going from just a pure quantum state to density matrix situation.
Yeah. Yes.
Matrix situation seems to be more general, and you see, after all, every quantum state is just one picked up state, while the density matrix kind of accumulates the knowledge about much wider possibilities of pure states, because
Yeah. So what you
in this context.
have you looked at my, not so long ago, maybe a month ago, I put out a paper on initial and final conditions, right? And arrows of time in quantum cosmology. Did you see that?
Well, if it was but just months ago, then definitely no, I did not see it.
Really? What's the matter with your internet?
Well, simply I'm not looking into.
I will send it to you.
Moreover, you know, that's, such things, the organization of this workshop was a kind of rather tiresome.
But I have a question for you. Did I do not justice, if it wasn't enough time, but was I said about your work on the density matrix okay?
Well, yeah, thank you very much for mentioning this, but I just want to see what's your opinion of this possible generalization, because you know,
It's very interesting, and I have to look further on it.